Okay. Now we are talking about a complete metric space, which means every Cauchy sequence converges in the metric space. That's what the completeness of a metric space is. And how about if a metric space is not complete? That's what we want to start on this remark today. If the metric space X D is not complete, then there is a unique complete metric space Y and D tilde such that the metric space Y contains the original metric space X, and the restriction of the metric D tilde on Y onto X cross X is same as the first metric D on the first metric space X, where we have the first metric space X here with metric D on it, and that's not complete, which means some Cauchy sequence in this metric does not converge. That's what that means, right? That's not complete, what I mean. That's not complete. That means some Cauchy sequence in this metric space does not converge to any. But we can extend this non-complete metric space to a complete metric space Y. That's what that means. That's what that remark says. Okay? If the original metric space is not complete, then what? There is a uniqueness. Unique complete metric space Y D tilde containing the original metric space X D. And then, if we restrict the D tilde metric onto X cross X on the subset X, then that must be same as what? The first metric D on the first metric space X. So that means Y D tilde is an extension of the original metric space X D, and Y D tilde, this extension is a complete metric space. And we say that the extension Y D tilde, the completion of the original non-complete metric space X. Where, for example, how about the set of all rational numbers with absolute metric? The set of all rational numbers, Q, with absolute metric, for example. I don't think this is a complete metric space. I don't think so. That's not complete. Then what is a Cauchy sequence? The rational Cauchy sequence which doesn't converge to any rational number. There are a lot of examples of what? Rational Cauchy sequence converging to some irrational number, right? So this metric space is not complete. But what is its extension to a complete metric space you have in your mind? Of course, the whole real number line with the same absolute metric, right? That's a complete metric space we already know, right? So this is the real number line. The whole real number line with the absolute metric is a completion of what? This non-complete metric space, which is the set of all irrational numbers with absolute metric. So that's a completion of the set of all rational numbers with absolute metric. That's a very simple example of that completion. Okay, completion. So no matter what metric space you have, if the original metric space is already complete, then that's all. We don't have to worry about that. But if it's not complete, we can extend that to some complete space containing it. That's what it is. Well, we have a very important result on a complete metric space, which is called the contraction mapping theorem. Contraction mapping theorem. Okay, contraction mapping theorem. That's a big theorem. Contraction mapping theorem. Let's let XD be a complete metric space. Which means every Cauchy sequence in this metric space converges to some number, some element in that metric space itself. Which means every Cauchy sequence converges, that's what I mean. And we have a map function T from the metric space X to itself. And suppose the map T is a contraction map from the metric space X to itself, which means there exists some number alpha between 0 and 1 such that distance between the function values of f, function values of t at x and y is less than or equal to the constant alpha times the distance between x and y for all x and y in the metric space X. So that's the definition of the contraction map. Okay, there is some constant alpha between 0 and 1 such satisfying this inequality. The distance between the two function values is less than or equal to that constant alpha times distance between the original values x and y. I'm not exactly sure about the distance between this contraction map and the Lipschitz condition. I don't know much difference between it. I believe they are actually the same things, right? Yeah. That's, the Lipschitz condition as well, right? Yeah. So over here, they say this is the definition of a contraction map. Contraction map. Under that assumption, then the result of that contraction mapping theorem says there is a unique x naught in the metric space X such that t function value at x naught is itself, which means there is a unique fixed point. There is a unique fixed point of that map, contraction map T. That's what that means. Okay, then that means x naught is a fixed point. Of the contraction mapping T. That's what that means. So that's a big result on a complete metric space, on a complete metric space. If you have a contraction map from a complete metric space to itself, then the result says that contraction map has a unique fixed point, unique fixed point. So we must justify two things, existence and uniqueness, both existence and uniqueness of that fixed point, of that contraction map, right? The uniqueness is much easier, okay? So let's describe the proof of the uniqueness first. To prove the uniqueness, we take two fixed points and what? Prove those two fixed points are identical, right? So how do we justify the uniqueness? Suppose there are two fixed points of that contraction map T. X naught and Y naught, both of them are fixed points. Yeah, suppose we have two fixed points x naught and y naught, satisfying both here. Then what happens to the distance between the 2 points x naught and y naught then? Because x naught and y naught are fixed points, that distance between x naught and y naught is same as the distance between their function values. But because T is a contraction map, we can apply this inequality for the next stage. So the distance between those two function values must be less than or equal to the alpha constant times what? The distance d between x naught and y naught. Then what does that inequality stand for? This number is less than or equal to some constant number between 0 and 1 times the number itself. Then what does that mean? That means what? Well, if we move this to the other side and then factor the distance out, then what? Distance between x naught and y naught times 1 minus alpha must be less than or equal to 0. That's what that means. Well, because alpha is between 0 and 1 strictly, what? 1 minus lambda is strictly positive. But the distance d between x naught and y naught must be greater than, non-negative, right? Greater than or equal to 0. Then what should we conclude? There is no other choice. The distance between x naught and y naught, this distance must be 0. Then. There is no other choice. Okay. So distance between those 2 points is 0. So what? By the definition of the metric space, x naught and y naught must be identical. So that proves the uniqueness of the fixed point. Okay? If we have two fixed points, then what? They must be identical. So that justifies the uniqueness of the fixed point here, which is much easier than the proof of the existence. How do we justify the existence then? Existence. we want to prove the fixed point exists. Okay? If we look at the definition of that contraction map here for T, then what? You already recognize the map T must be what? Continuous. Because that's a Lipschitz function, right? So you already recognize the contraction map T is a continuous function from the metric space X to itself. So we can apply the continuity condition to the contraction map T. We note that the map T is continuous. Okay, continuous. Actually, the map T satisfies Lipschitz condition. Lipschitz conditions with constant C is equal to alpha. So we can use what? The sequential criterion for the continuity of the function map T to generate a fixed point for the proof of this existence. So how do we define a sequence to use the sequential criterion for the continuity of the function T then? Well, here is the following. Define a sequence x of n in X inductively as follows. The first term of the sequence will be free. That's your choice, whatever you like. What I mean is, let's let x of 1 in the metric space B, metric space X, be arbitrary. So we can take whatever point we like for the first term of the sequence on the metric space X. And then let x of 2, the second term of the sequence, be the function value of T at first point x of 1. And let's let x of 3 be the function value of T at x of 2. Keep going on this way. So keep applying the map T to the previous term to get the next term of the sequence. That's what that means. Keep going on this way, and then in general, n plus 1th term of the sequence must be the function value, T function value at the previous term, which is the nth term of the sequence, etc., etc. Then do you have much idea about this sequence here? We must claim this sequence we just generated is a Cauchy sequence. Yeah. Then we are ready to apply the completeness of the metric space X. If we justify the sequence we generated there is a Cauchy sequence in the complete metric space X, then what? That Cauchy sequence must converge to some number, right? The some number will be the fixed point we want to generate. Yeah, that's what's going on, okay? That's what's going on. Yeah. So our claim over here is that what? The sequence x of n we just generated here is a Cauchy sequence in the metric space X. Okay, that's what we want to claim. Yeah, its justification is very much computational. Its justification is very much computational. Let's let index n is more than the other index m, where both n and m are natural numbers. Natural numbers. Then, what must be happened to the distance between the corresponding terms of the sequence x of n and x of m. By the definition of the sequence x of n, that's same as distance between the t function values at x of n minus 1, the previous term, and t function value at x of m minus 1, which is the previous term, right? That's what it is, by the definition of the sequence x of n. And then that's less than or equal to, because t is a contraction map, right? The distance between those two function values must be less than or equal to the constant alpha times distance d between what? X of n minus 1 and x of m minus 1, right? Keep going on this process. What is the next step then? Okay? Let's continue this process. Let's continue this process. Then what happens? That's less than or equal to alpha times distance between x of n minus 1 and x of m minus 1 is what? Again, less than or equal to what? Distance between, okay? Yeah, that's exactly equal to. Yeah, again, by the definition of our sequence x of n, the distance between those two terms is equal to distance between function values at x of n minus 2, the previous term, and the function value of t at the previous term x of m minus 2. That's what's happened. Then again, because t is a contraction map, so what? The distance between those two function values must be less than or equal to what? Another alpha times what? Distance between x of n minus 2 and x of m minus 2. That's what's happened. So that must be less than or equal to alpha squared times distance between x of n minus 2 and x of m minus 2. We continue this way. Then, if we continue this way, then that whole must be less than or equal to what? Alpha to the power m minus 1 times distance d between x of n minus m plus 1 and x of 1. That's what we will have, okay? At the end, if we continue this process, that's what will be happened. Then I believe the next step is to apply the triangle's inequality to this distance. Yeah, this distance is less than or equal to, that's by the triangle inequality. Yeah, by the triangle inequality, this distance is less than or equal to, let me write it out. Distance between x of 1 and x of 2 plus distance between x of 2 and x of 3 plus distance between x of 3 and x of 4 plus etc. Plus finally distance between x of n minus m and x of n minus m plus 1 by the triangle's inequality. Then let's apply the definition of the sequence x of n again on all the terms here other than the first one. We keep the first one and then apply the definition of the sequence x of n to all other terms. If you apply, okay, the definition of the sequence x of n, and again what? Contraction map for the function t. Then what? Each distance is less than or equal to some alpha constant multiple of some others, right? Well, this first distance will be less than or equal to alpha constant times distance between x of 1 and x of 2 plus the distance over here, the distance between x of 3 and x of 4 is less than or equal to alpha squared times distance between x of 1 and x of 2. So keep going on this way up to the last distance. The last distance is less than or equal to alpha to the power n minus m minus 1 times distance between x of 1 and x of 2. Yeah, that's what will be happening. Okay? If we apply the contraction, the inequality there, plus the definition of the sequence x of n together, then that's what will be happening. Okay. Then distance between x of 1 and x of 2 is in common, so let's factor this out. And then the leftover is 1 plus alpha squared plus up to plus alpha to the power n minus m minus 1. That's what's happened. Then the same as alpha to the power m minus 1 times distance between x of 1 and x of 2 times what is the computation of these sums inside the bracket. That's kind of a geometric sum with multiplier alpha. So that's same as 1 minus alpha to the power n minus m divided by 1 minus multiplier alpha. That's what it is for the sums of the numbers inside the bracket there. But this number over here at the top is less than 1 because alpha is less than 1, right? So let's continue up there. Okay, so the whole thing over here is less than or equal to alpha to the power m minus 1 times reciprocal of 1 minus alpha, because this top portion of the fraction is less than 1. So less than or equal to reciprocal of 1 minus alpha times distance d, distance between x of 1 and x of 2. That's what's happened. Okay, what happens to this as m goes to infinity? If both n and m approach infinity, then what happens to this? Because alpha is less than 1, alpha to the power m minus 1 approaches 0. So the whole thing must approach 0. That's what must be happening. So if two indexes n and m are approaching infinity, the distance between the corresponding terms x of n and x of m approaches infinity as well. Approaches 0 here. So what does that mean? That means what? The sequence x of n we generated is a Cauchy sequence. So the sequence x of n we generated here is a Cauchy sequence. That was what we have justified. So we got a Cauchy sequence in a what? Complete metric space X. We got a Cauchy sequence X of n. Okay? In this complete metric space X, so what? The Cauchy sequence must converge to some number X not in the complete metric space X itself. since the metric space X is complete, there is some point X naught in the complete metric space X such that the Cauchy sequence we have generated X of n converges to the point X naught. Then what happens to the function value of t at x naught, the sequence X of n converges to? We want to show that the function value of t at x naught is what? X naught is self. That's what we want to claim, right? How do we claim this equality? We will have to use the continuity of the function t then, which we haven't used yet, right? Did we use the continuity of the function f, function t yet? I don't think so. So it's time to use the continuity of the contraction mapping t to claim the equality of these two here. Okay. Since the mapping t is continuous, the function value of t at x naught is same as what? That's actually same as what? Function value of t at limit of x of n sequence we have generated. But because t is continuous, right? Then the mapping t value and limit are interchangeable, right? Yeah, that's x of n is a sequence converging to x naught. So what? Because t is continuous, the function value of t at x naught is same as what? Must be same as what? Limit of the function value of t at the sequence x of n. Because t is continuous. So x of n converges to x naught. So because t is continuous, t of x of n must converge to what? T of x naught. That's what that means. But by the definition of the sequence x of n, the function value of t at x n is same as what? The next term of the sequence, which is x of n plus 1. What happens to x of n plus 1 sequence when n approaches infinity? That converges to x naught itself, right? So we have justified that what? The function value of t at x naught is itself. That was what we have justified, which means x naught in the metric space X is a fixed point of the contraction map T. Yeah. So we have justified the existence of a fixed point of the contraction mapping T. Any questions or any comments on this? So that's a big result which is applied to the existence of the solution of ODEs and PDEs theoretically. Yeah. I hope I would have some chance to introduce some application, ODE and PDE applications of that contraction mapping theorem sometime in the future. The differential equation is an applied analysis kind of thing, right? Yeah. So we have to hire a lot of hard analysis stuff to justify the existence of solutions on differential equations. Okay. You already know that if we have a normed space, then that generates a metric space. And if we have a metric space, then that generates a topological space. And the real number line with the absolute value is an example of a normed space. Actually, yeah, that's the special case of the n-dimensional Euclidean space with the norm, right? Distance norm. And then any n-dimensional Euclidean space with the norm here is a special case of a normed space. So then, yeah, I want to introduce some examples about the normed space on the next step here. And normed space here is in the middle of what? The Euclidean space and then metric or the topological spaces. So then that's a very important space. Normed space is a very important space between the Euclidean metric and then general metric there. So then let's focus more on the normed space here in the next step. Then I want to introduce a couple of different examples of normed space. Let me remind you of the definition of a normed space first. You have already studied in the assignment problems. To be a normed space, first of all, that must be a vector space. A vector space. You have studied in linear algebra. X over the whole real number line R with a map that's a map from the vector space X into the set of all non-negative real numbers satisfying the three conditions. Satisfying the three conditions, 1, 2, and 3 is called a normed space. Yeah, that's the definition of a normed space. So to be a normed space, first of all, that must be a vector space with a map from the vector space itself to the set of all non-negative real numbers. And that map must satisfy those three rigorous conditions. First of all, okay, norm of x is equal to 0 must be equivalent to what? The element x must be 0. And secondly, norm of some constant multiple of the vector x, because that's a vector space. So x is a vector space. X is a vector in the vector space x. And then the norm of any constant multiple of the vector x must be same as absolute value of the constant times the norm of the vector x. For any vector x and constant c on the real number line, and the norm of addition of two vectors must be less than or equal to addition of norms for any vectors x and y in the vector space X. That's a kind of a triangle inequality, right? You have already experienced a lot in the past. Triangle inequality. So norm of addition is less than or equal to addition of norms. So if a vector space with this map satisfies those three rigorous conditions, then we say that the vector space is a normed space. Okay, normed space. You already know this note. If we have a normed space X then how do we generate a metric space from this normed space? You already know. If we have a normed space X and if we let distance between the two vectors X and Y be the norm of the difference between those two vectors, then the normed space X with the d distance function makes a metric space. Which you have already justified in some assignment problem, right? In some homework problem, you have already justified that. Yeah. And then you also have the following inclusions, right? If we have an inner product space, and that's a special case of what? The normed space. And if you have a normed space, that's a special case of a metric space. And if you have a metric space, that's a special case of a topological space. Right? Now let me introduce a couple of different examples of normed space then. L1 norm. That's the first example I have here. L sub C1 at the whole real number line R. This is the set of all continuous function f from the real number line to the real number line. Such that integration of that absolute value of the function f from on the whole real number line is finite. Yeah, that's the definition of L sub C upper 1 at the whole real number line R. Yeah, that's the collection of all continuous function, continuous and integrable function on the whole real number line. That's the set of collection of all continuous and integrable function on the whole real number line R. We say that the function f is integrable on the whole real number line R if what? If this improper integration of absolute value of the function f on the whole real number line R is some finite number. Yeah. Then let's define a norm on this set X. So let's let so-called L1 norm of the function f on this collection be just that integration. Which is a finite number, right? Then we claim that this set with this map we have just defined makes a normed space. The proof of this claim is quite easy, you know. That's quite much straightforward for you. Yeah, then we have to continue this proof next week.